Welcome everybody to this first session of the Quantum Mobile Networks seminars. I'm very happy to be able to be here today and host this event, which is organized together with several universities internationally. So I am Antonio Di Maio. I'm a postdoctoral researcher at the University of Bern, working in the communication and distributed systems groups, led by Professor Brown. And before starting, I want to acknowledge the support and thanks all the people who made this event possible. So first of all, I would like to thank the University of Bern, who has sponsored and supported the virtual exchange program. This program aims at offering the students an experience of study exchange without necessarily having to leave their home country. So this program originated during the pandemic, as you might imagine, but due to its success, then the university decided to keep it. I want to also thank Professor Brown for encouraging me to apply to this program. So we eventually got supported by the university. Initially, this program was tailored at subjects that are managed and are the core subject of the groups. But I want to thank also Professor Tasley, who suggested to add aspects of quantum communications to the topic of the seminar, making it more interdisciplinary. I also want to thank Professor Sequeira and Abelin for the intense activity of dissemination and for having gathered the interest of so many students from the university in Brazil. And I also want to thank Professor André Stefanov, who is today here with me, that spent a lot of time to help me to fine-tune and improve the scientific quality for the for the topics of the seminar. And I also want to thank all the other advisors and the supporters who gave their invaluable contribution for and feedback for preparing these seminars. So yeah, as I said, this initiative, I'm not alone in this, but there is a large team of excellent researchers who are advisors for the seminar. So this is a moment that is particularly important for the students, because you need to understand what is the research topic of each advisor. So in case you have doubts, you could contact the right person. So if that's okay with the advisors who are here, I would like to have them introduce themselves very quickly. Just a 30-second introduction round for the advisors who are here online. And just your name, your affiliation, and your research activity. So we could start from Professor Abelin, if he's online, is connected.
Are you hearing me?
Yes.
Oh, thank you. Okay. Sorry, because I'm in a place with a lot of noise, but my name is Antonio Belém. I'm a full professor at Federal University of Pará. I started to work with quantum communication and quantum internet to study, in fact, when I was vice professor with Professor Don Tosley. So now we have a project in which we are investigating new protocols, routing protocols for quantum communications and quantum internet. That's it. Thank you, and good seminar for everyone.
Thank you. We could move on to Professor Marica Madeo from the University of Mediterranea of Reggio Calabria, Italy.
Yes. Hello, can you hear me?
Yes.
Okay, thank you. Well, yes, my name is Marica Madeo, and I am an assistant professor in telecommunications at the University of Reggio Calabria, which is a very small town in the south of Italy. I'm very happy to virtually meet you today. My major research interests are in the fields of edge computing, wireless ad hoc, and vehicular networks, and information-centric networking. So my expertise is mainly related to layer 2 and layer 3 protocols. And honestly, I currently have no strong background on quantum networking, so I think this will be a very special occasion for me to learn and study about this paradigm. Thank you.
Thank you so much for the introduction. I also want to point out that here we made sure to select, let's say, a committee of advisors with very diverse backgrounds. So obviously we don't expect all of them to have full knowledge of all topics, but here really the strength of the seminar is really bringing together a lot of experts from different fields. Professor Campolo from University Mediterranea of Reggio Calabria.
Okay, hello everybody. I'm from the same university as Marica. I'm an associate professor there, and my background is mainly on vehicular ad hoc networks and also on 5G and beyond systems. As Marica, we don't have this strong background on quantum, and we hope to learn a lot as our students, hopefully. Thank you, bye.
Okay, then it's me. So as I said, I'm a postdoc in the University of Bern, and my main interest at the moment is modeling of mobile ad hoc networks, especially in terms of performance and in terms of throughput and delay, especially applying data-driven methods, for example, machine learning for prediction of the performance. But I also work on other topics, such as the distributed machine learning, still on keeping an eye on mobile ad hoc networks, and gossip learning, split learning, and related areas. So that's it for me. And now, especially with the new potential of quantum communication, who we will see for the remaining of today's presentation, very interesting to understand what could be the potential impact of these new quantum channels on the performance of the network. So we could move on to Professor Engel from the University of Luxembourg.
Thank you, Antonio. Yes, I'm here. So my name is Thomas Engel. I'm professor for computer networks and telecommunications at the University of Luxembourg since some 20 years, bit more than 20 years. Application fields mainly in the area of automotive communication, so in-car and car-to-car communication, and then distributed networks there.
Thank you so much for your introduction. And then we could move on to Professor Rizzo from the Technical University of the Southern Western Switzerland.
Thank you, Antonio. So I'm Gianluca Rizzo. I have a double affiliation. I am at HSSO Valais in Switzerland and the University of Foggia, Italy. And my interest, the closest interest to the topic of the seminar are, floating content and gossip learning, vehicular communication. I didn't work, so far I didn't do much on quantum communications, but I'm very much intrigued by the topics of this seminar.
Thank you for your introduction. So now we can move to Professor Stefanov, who's obviously here, so he could provide information
in the background. So I'm from the University of Bern too, but I'm from the Institute of Applied Physics. So I'm working on quantum optics, the experimental quantum optics, so mainly using quantum states of light for metrology, developing new measurement scheme, and also on quantum communication. So this is generating the right quantum states of light for new communication protocols like quantum cryptography.
Thank you for the introduction. Finally, I would like to invite Professor Tasley to introduce himself.
I'm Don Towsley. I'm a professor at the University of Massachusetts in Amherst. I've been working in the area of quantum networks for about 5 years, and my focus is on protocol design, optimization, analysis, and control of these networks.
Thank you so much for your introduction. All right, so now that we know each other and the students have understood the skills and the domain of each of the advisors, we could take a look at why we are here, actually. So what's the motivation behind the seminar? Why did we want to consider technologies that are apparently far away from each other? So first of all, especially for the students who have in mind a career in industry, there is a big economic potential for joining of these two technologies. McKinsey forecasts that quantum communication as a field will generate $8 billion per year in revenues by the year 2030. However, despite funding, which also is consistent from governmental and industrial parties, there is a big talent shortage in quantum experts. So this is gives the perspective to students and in general practitioners that there is a lot of need for quantum experts. We see that in the world, the major players here are China, Europe as a whole, and the USA, who are investing considerable funding in it. We know recently China has launched a quantum satellite and has established a working quantum key distribution secured video conference between Beijing and Vienna. And so this leads the path to much more consistent funding in the future, which is still a contrast with the lack of people who are skilled in quantum technologies in general, and in particular quantum communications. In particular, quantum communications have a big potential due to two main features of the links, which are security and throughput. Why are quantum links secure? Because a malicious user or an eavesdropper or a party who would be interested in capturing the information transferred over this channel wouldn't be able to do so, because the simple act of observing the information moving along the quantum channel would mean destroying it. So the legitimate parties would be aware of the attempt for a malicious user to read the information exchange on this channel. And so this leads to quantum key distribution protocols who allow the two parties to safely share a secret. The other important aspect is the higher throughput. So there is a principle that is called quantum dense coding, which allows two parties to send two classical bits by transferring only one qubit, provided they exchange some entangled state beforehand. So with this point, we really understand that there is a huge potential of quantum communications. It is also well known that the classical properties of mobile networks are relatively well understood, but what is not understood so far is what impact could have replacing the classical link between mobile nodes with links that rely on quantum principles to exchange information. So we performed a literature review, and we identified a set of topics who could have a potentially large impact, which are at the interface between the quantum communications and mobile networks. Indeed, here we could see 8 topics, but this is not restrictive. There are many, many other topics that could be identified. And these will be the topics that we are going to treat during these seminars. We can go through them very quickly. We don't have the time to discuss them extensively, but all the information you could find it in the syllabus, which is already published in Ilias. We will discuss the technical aspects at the end of the presentation if you have access or not yet to the platform. So the first topic, or the first two topics, are very much closely related to the physics aspects of the quantum channels. So the first topic is a physical implementation of quantum channels. So normally, nowadays, what scientists can do is exchanging information reliably over optical links. However, for mobile nodes, it is unrealistic to have them exchange information via optical channels. So we have to exploit microwaves, for example. However, it is much more difficult to exchange quantum information over microwave channels due to an effect called decoherence, which in short, we could say that the probability of successfully exchanging a quantum state or entangled state decays exponentially with the distance between the parties. So that could be it's a promising research path. For example, if we want to keep in the optical domain, it could be interesting to research how the exchange of information via optical links between satellite or satellite ground, or also to deliver this information via flying platforms such as drones. So this is for the first topic. So then another interesting topic would be the simulation tools. So to validate algorithms and the protocols and methods on quantum mobile networks, we have to simulate them. So this scientists have proposed a large set of simulation tools, and this topic for the students could be investigating pros and cons and suggesting or showing a little demo about it. Then about media access control protocols in quantum mobile networks. So especially for the students, or for who doesn't know, media access control protocols are needed for guaranteeing that mobile nodes access the channel without creating interference, so destroying each other transmitted information at the receiver. So this is well studied in the classical networks, but is not well understood when the links are quantum. Similarly for routing, so it's a topic that deals with moving some information from a source to the destination using intermediate node as relays. So this is also well studied in the classical networks, but also is an open field when the links are quantum. Since the quantum links have specific physical properties, also when we replace classical links with quantum links, this will impact heavily the performance of the network as a whole. And this leads to the fifth seminar topic. Especially here in the fifth topic, the keyword buffering is important, because in order for intermediate nodes to store quantum states reliably, we need to use quantum memories, which have properties that are radically different from traditional and classic memories. Then the last three topics are gossip protocols in quantum mobile networks, age of information, and mobility patterns. So each of these are well understood in classical networks, but not as well if the links, again, are quantum. With gossip protocols, normally are those type of algorithms that try to perform a global operation with opportunistic contributions by the different elements of a system. Age of information deals with optimizing the trade-off between transferring and broadcasting information so that at the receiver, the freshness of some information is maximized. And the mobility patterns effect on classical networks, again, is very well studied, but it's not well understood how this can impact, for example, the establishing of quantum links between mobile nodes. However, as I said, these are not exhaustive, is not an exhaustive list of topics, so you could feel free as a student to suggest more topics that may suit your liking more closely. So now on the technical aspect of how this seminar is gonna be structured. So we have a list of topics, and each of this topic will be associated to a presentation each week. The duration of each presentation is 30 minutes plus a following question and answer. And yes, will be given by a group of students that will be arranged next week. So the students could take inspiration from a dedicated mini literature review associated to each topic that you could find in the syllabus if you have already seen that. And starting from today, all this session will be recorded, so you have to also let me know if you wish your session not to be published, or if you're okay with it. Let's do it opt-out. I estimated that the total effort for this seminar will be 5 ECTS, which corresponds to around 150 hours of workload, which you could see here on the right, a potential breakdown between like 40 hours making slides and 48 hours of self-study and so on. So that's just a recommended breakdown of the effort. Then for the students, especially from Bern, who need the ECTS, you need to provide an attendance of at least 80%. And then at the end of each session, you should rate the presentation from your peers via a Google Forms link, which I could show later on. Following the grading rules that you find in the syllabus. We can also discuss this later. So this obviously is just a consultation for me, and also an exercise for you to develop your critical thinking, but obviously it will not have it does not have to be taken into account to compute the actual final grade. Each presentation, each presenter, or actually each group of presenters will have to prepare 3 questions associated to their topic, to their presentation each week, that I will upload on Ilias, so that the other participants have to answer on the platform by the following Wednesday. So if we present on Friday, by the following Wednesday, you should upload the answers to these 3 questions, this to account for the attendance. And then to support active participation, you will get a tenth of a final grade for each question that you ask during the question and answer session, just to stimulate the critical thinking from the students. So what do we want to achieve from this seminar? We want to support and foster independent study skills from the students. However, just keep in mind that all the advisor will be there to support you if you have questions about the papers that you are reviewing or any other material. And this is important, and that's why we have introduced the advisor before. You can target the questions to the expert in the field of the question you have. Then also we want to support and foster critical thinking. So that's why I recommend, and I added this aspect of peer grading or peer evaluation, and also supporting clearly your presentation skills. It's also important you learn to identify independently research directions, who could also lead to writing a bachelor or master thesis with some or more than with one or more of the advisors of the seminar. And then as a more broad goal, we would like to spark some academic collaborations between the universities involved. So in the second part of today's talk, there will be an introduction to quantum provided by Professor Stefanov. So this is the final part of my presentations today. So the conclusion and also the task for next week. So the students should skim read all the literature that I have uploaded on the Zotero group. You should ask for access to this Zotero library. So there you find all the downloaded and organized papers associated to each topic. Then I would like you to express a preference on each topic by accessing the Google Sheet that you find at the link in the slides. I will obviously share these slides. And then next week, I will collect this preference from your side, and then we will form the groups. And then if we cannot finish today with the introduction to quantum, then we will finish it next week. The best way to interact with us will be with either during online session, you can just raise your hand and we will just be there to answer your questions. Or also a good way is by posting a question in the Ilias forum, so that the advisors or the best fitting advisor could give you an answer there. If you have a very specific problem or a personal matter, you can also contact the advisor directly via email. Ilias allows you to contact each course member directly via email. By now, all the external members should have received the credential to access the Ilias course. If you haven't so far, you can contact Samuel Iniger from the Ilias support team. Another important thing that I really care is some sort of a continuous improvement. So each session will be associated to a Google form through which you can provide anonymous feedback to me. So obviously, if you have some aspect you really liked and some aspects you really did not like, I would love to hear it, so we could either fix it on the fly, or for sure for the following semester it will be taken care of. So this is all from my side. Do you have any questions or any doubts about, for example, the topics or the procedure of how the seminar is gonna be organized? So for the students, you should be able to see like a browser. So here in the Ilias webpage, you just access the main page of the forum, of the main page of the seminar, and then you just click on the exercises. And then after each of the seminar talks, you just click here. Here you will find the, of course, I will replace this with the question associated to each talk. And then you just click here to edit text, and then you can answer your reply. So that's sufficient for your weekly assignment. So yeah, here at the end of each presentation, you are able to add the grading from poor to exceptional following the grading guide, and then you can just submit it. Yeah. And finally, let's see. Yeah, the Google Sheets for expressing your preference for the topics. Yeah. Yeah, here you see there is each row corresponds to a topic. So here I put myself, like my name, and then you just put 1, 2, 3 according, like you list your preference. And then next week we will group you, and then from then you start preparing your presentations. So any last question before we move on to the introduction to quantum? Otherwise, we are good.
I'm sorry, what exactly do you mean by the preference?
By the reference?
The preference.
Ah, the preference, yes. So after you read about the literature, so you could sort your preference from the topic you would like to have most from the one you would like to have the least.
Oh, okay.
Yes. And then the students will be grouped according to their preference. All right, so I guess it's time for moving to the second part of our presentation, is the introduction to quantum. Thanks.
So, as I said, thank you. So the idea is a little bit to have a kind of short introduction to quantum physics for those who may not be completely familiar with it, coming from the computer science field. So I guess for those who are familiar with quantum physics, that may be a little bit too easy, but we try to, let's say, set the level kind of similar for everyone. So the question is, what's quantum? So of course we have, take the mouse. Oh, okay, no, I take that. We have physics, law of physics, so range from quantum, let's say, physics describing usually small objects like molecules, solid states, semiconductors, and that goes into physics, which describes, so classical physics describing big objects like biological stuff. And so in between we have complex, for instance, molecules, and the question, one kind of fundamental question of quantum physics today is if there is a border between those laws, and where is it? So it is not yet not solved. So from the operational point of view or technology, there's also differences. So you have devices like a candle, which can be quite well explained by the laws of classical physics. And other, like here, this is a commercial device of quantum cryptographic system in optical fiber, which relies strongly on quantum physics. And of course, in between, you have things like the laser. So a laser device in itself, to understand how the laser light is produced, is a quantum process, but the laser light itself can be described by classical physics. And here where the border is, then this depends on your funding agency and how you want to sell your objects. So from the side of the computer science, there's kind of well described border between classical computer, as described by the Turing machine, and a quantum computer following the law of quantum physics. So nowadays, there start to be some quantum computer, but they still have a very low number of so-called qubits, which do not make them for the moment kind of universal quantum computing, at least useful. So here we try to answer a few questions. So what is quantum physics? What are the photons? Because as we are speaking mostly of quantum communication, and for quantum communication, as for classical communication, light is the main carrier of information. One important concept in quantum physics and in quantum communication is entanglement related to non-locality. So we shortly see that. How can we prove that we have entanglement, and what is it good for? So quantum physics, as I mentioned, are the laws of physics describing nature at a microscopic scale. As I say, applied for since many years on many systems. And this is kind of called quantum 1.0. And related to that, there have been a lot of experiments related to more fundamental aspects, not technological, but what is locality of nature, what is determinism, or even reality. And since maybe 20 years about, there's so-called quantum 2.0, which is still the same quantum physics, but the idea is now we are able to manipulate single quantum objects and to make use of their properties for technological purpose, mainly, like quantum communication, or quantum metrology. Now coming back to classical physics, so before introducing quantum physics, what is classical physics? So in every, let's say, classical physics systems, so you have objects, and those objects, they have well determined states at each time. So this ball here is following a parabolic trajectory, and at any time it has a position and a velocity. The same if you have a field, electromagnetic field, the state of the field, so the value of the field at each time and each positions are well defined. Or if you had a computer, then the register of the computer, of the memory, are well defined states of the memory in bits. So if we assign to this point-like particle position and velocity, so this is represented by some number, a state vector, And there is an evolution which is described by some differential equation, in that case here, Newtonian or Hamiltonian evolution. For fields, again, you have a value which is defined at each position and each time, so given by the vector of the electrical and magnetical fields, and the evolution of those fields are described by equation, which here will be the Maxwell equation. For a computer, you have bits, and the evolution is just given by the program. If you move to quantum physics, then the system itself is described by a wave function. So it's a function of position and time, and this wave function evolves in time. And for instance, it can broaden, and this is related to the Heisenberg uncertainty principle, so that the position of the particle is not exactly or perfectly defined. So, but as it is a wave, so to say, although superposition of waves are also a valid state. So if you take two states, then the sum of those two states is also a valid state. So in that case, here you have the particle being either going to the left or going straight through that semi-transparent mirror. So in general, any quantum state is represented by such continuous function or by a vector in a complex Hilbert space. So is the vector here, this notation called the bracket notation introduced by Dirac, is just to tell us that you have a given vector psi, and it's given in some basis given by the vector basis vector I with coefficient Ci. So this Ci are the numbers representing the states once you have defined the basis state I, and those numbers are complex. For instance, in that case of that particle going to the left or straight or to the right, then you have a superposition psi which is left plus right. And so you have coefficients in front which are such that the state is norm to 1, which means the square of the coefficient, the absolute value square, the sum of the absolute value of the square of the coefficient, it should be 1. We'll see later on why. So the states undergo some evolution, and again we need an equation describing the evolution, and this will be given by the Schrödinger equation, which is a deterministic equation to provide the state evolution. So you can solve that differential equation relating the evolution operator, time operator u. So u at time t gives you what you need to compute the state psi at some later time, knowing the state at time 0. And to get this operator u, you have to solve that equation here, where h is an operator called the Hamiltonian operator, which represents the energy of the system. So now from this classical description, valid for particle, fields, or bits, we have to move to something else where the properties now are not well defined, because in quantum mechanics you cannot tell that one particle has a well-defined properties like position or velocity or momentum. So what is well defined is the state of the particle, and we know the evolution of it under the Schrödinger equation. If you think of quantum computer, then the state of the computer will be a superposition of qubits, qubit being a superposition of 0 and 1 with arbitrary coefficient alpha and beta. And if you have n of them, then you have the tensor product of all those different possibilities. And the evolution is given by a program, but now the program will follow the law of the quantum computers. So it's kind of blurry between the superposition of 0 and 1, so you cannot assign anymore a well-defined value to any to all of the bits. One thing, sorry, which is missing now, it's, let's say, the properties, because at the end of the story we do measurement and we get a velocity, let's say, or a position for one particle. So, and because as I mentioned, they are not defined in advance, so they come from the measurements. So now if we have this again, this particle going through the beam splitter, so a semi-transparent mirror, at the end, where is the particle? Do we measure it on the right or on the left side? So the property only appears when the measurement is performed. And here there is an additional law let's say, axioms to quantum physics, which tell us that the probability of an occurrence is given by the wave function, by the modulus square of the wave function. So the probability, for instance, to detect a particle at position x at time t is given by the modulus square of the function psi, the wave function. So if we look in the case of discrete function, as I mentioned before, given by a set of complex number, so this probability to measure the particle being in the state I, which will be here right, left or right position, is given by the product between the state psi and the end state I, corresponding to the particle being left, for instance, and modulus square again. So if we look in that specific case, the probability to be left will be the product of left time psi, modulus square. So now psi, if I just come back, I had written it, oh, sorry, here as left 1 over square root of 2 left plus 1 over square root of 2 right. So I replace it, sorry, here. So the modulus of 1 over square root of 2 is 1/2. So if 1/2 times left product right or plus left product left. Now left product right are orthogonal considered states, which means so either the particle is left or right. So the product of both is 0, whereas the product of left with itself is 1 because the states are normed. So they are such that their norm is 1. So this given 1/2, the same for right will be again 1/2 in that case. So knowing that the wave function is more, it's actually the wave function in the quantum theory as it is now is more than just the fact that we don't know something about the theory. It's really the state as known by nature, so to say. And it's also more than just a classical probability distribution, as we will see, because we get results which cannot be explained by just classical physics. So, and because you can have superposition of states, then it means that the particles also interfere. You can have the system, the process of interference when you have superposition, like you have waves, let's say, on the surface of a lake. They will interfere, and you see that you have places where you have destructive or constructive interference. So the wave function also can interfere. So, and this is, for instance, the case. If you take one particle, you can split it and then recombine it, and then this could lead to interference. So this is usual with light, actually, because we know that light is a wave, even classically, but this is valid for any particle, any component or physical component. So as physical system, it has been demonstrated that you can see interference of neutrons or atoms in a cold state, so called Bose-Einstein condensate, or even large molecule could show interferences. Or, for instance, current in superconductor could also show interference. Actually, such systems are used to implement qubits in today's quantum computers. So there's obviously a problem because I say, this is valid for anything. So this was already seen by Schrödinger in the early days of quantum mechanics, that if this is valid for one electron, one molecule, so where does it stop? So he had some thought experiment. We say, okay, here you have a quantum system. So in his thought experiment was the disintegration of a radioactive particle. And this quantum system could trigger a hammer breaking down some bottle with poison, and then this is in a closed room, and there's a cat, and the cat will die if the poison is released. So now this quantum system could be in a superposition of, let's say, being disintegrated or not. So should also be the hammer in a superposition of breaking the bottle or not, and so also at the end should be the cat in a superposition of being dead or alive. So this is just to illustrate that this border I was mentioning at the beginning, that we don't know exactly where it is because we never observe such a dead or alive, at the same time dead and alive cat. The open question is there really a fundamental question, or Is it the fact that we don't observe such a cat related to the fact that it's very difficult to do let's say, quantum experiment with macroscopic objects because of a concept of decoherence, which means as soon as the wave function in superposition interact slightly with something else, it could then decohere, so it could lose its superposition properties. This is actually such technological problem which restrain, or let's say, the fact that we can have for the moment very large quantum computer, because it's difficult to put many quantum objects into superposition. Now, if we come back to, we go to light. So as I mentioned, for quantum communication, light is an important device because it's a carrier of information. And historically, it was always the question if light is a particle or a wave. So see, until the end of or the beginning of the 20th century, it was well established that light is a wave, and there was a well established electromagnetic theory after Maxwell's equation. Beginning of the 20th century, so those people, Max Planck, Einstein, Dirac, and others, realized that you have some experimental results that you cannot explain using purely electromagnetic theory. And there is something like the quantization of light, which means that light only, the energy carried by a light beam is only a multiple of some quantity, which is essentially the frequency omega of the light times some constant, the Planck constant. So, and those quanta of light are what we call photons nowadays. So if you then can really look at one of those single quanta or single photon, then you have so-called quantum light. So you have quantum states of light that cannot be explained by Maxwell's equation. Those are, for instance, so-called single photon, or if you have several of them in different states, quantum correlated, they are entangled photons. These are other squeezed light, which is kind of, you have many photons, but in a state which is not described by usual electromagnetism. Light has an advantage that if you want to test some quantum theory, it could be relatively easy to perform experimentally. Light, you don't need vacuum systems or very cold systems. So it can be distributed over a large distance. So that's why it is useful for fundamental tests, but also for quantum information. And also light is a common tool usually for measurement. So it plays a big role in quantum technology for quantum measurements. What are single photons? Maybe just to mention. So single photons are particles of light. So they have no mass, but then they carry some degrees of freedom, which are not so much. Actually, it's polarization, which corresponds to the polarization of light classically. Their energy and their time of emission, and their position and their momentum. So if you have a light beam, for instance, you can think, so what is its energy, its frequency or color? If you have a pulse, when was it emitted, and in which direction was it emitted? And also, some degree of relevant degree of freedom is the number of photons, because you can have light state with only one photon, or with many photons, or even distribution of photons. The photons can be created or annihilated, so that's why you have sources and detectors of photons. Typically, so if you have one photon, so one photon which is polarized at 45 degrees, so this could be written as superposition of a photon polarized horizontally or vertically. If you send it on a polarization beam splitter, then again, with 50% chance you will be reflected, or you will detect it being reflected, or you will detect it being transmitted. So actually, this kind of device could be used to generate a random number, for instance. And those numbers are purely random because they really come from quantum randomness. So in general, it's not necessarily 50-50, so you can have alpha and beta as coefficient here in front. And the probabilities, as I already mentioned, will be given by alpha square or beta square. So Again, there's several types of light, so you can have light with only one photon or with only two photons, or state of light with a given number of photons. If you think of the laser light, so coming out of a laser, from a laser, that will be a distribution, that will follow a distribution of the photon number. It means if you can measure how many photons are in a laser beam, you will find some variability in the photon number. And this is what usually is called shot noise. This is true for laser, but also for other classical light sources. And the shot noise, maybe it's the fundamental noise limit. For instance, if you take pictures and you have very good sensor, or in communication, if you have low signals, then you will at some point be limited by the shot noise. Even if your electronic is perfect, that will be the ultimate limit. You can distinguish those kind of type of light by the so-called Hanbury-Brown twist intensity interferometer, which essentially measure the correlation, so the probability to have measurement between the two arms, let's say, after the beam splitter. And it can be seen that for single photon, this product of the intensity or of the probability is zero, because the single photon can only go up or being transmitted. Whereas for classical light field, you always have a little bit of light in both arms. Now, what if we go from 1 to 2 photons? So now we come to combined system, and this is important for the concept of entanglement. So if we have 2 photons, again, each of them could be horizontal or vertical. So we have 4 possibilities. So both photons horizontal, both verticals, or one horizontal, the other one vertical. So as I mentioned, any superposition of those states is still a valid quantum state. So this superposition here of the 4 possibilities is a valid quantum state. So there are many of such superpositions depending on the coefficient. And move to the next. Sorry, okay, PowerPoint is stalled. Okay, now it's good. So one of those superpositions will be the following. So we can think of having both photons horizontally polarized or both photons vertically, a superposition of those 2 states. So this state is an entangled state, which means we cannot write this state as the product of photon A being in a specific state and photon B being in another state. So this means that the polarization state of each photon is not defined before the measurement. So if we do a measurement, we may find HH or VV. So then we know after the measurement, the polarization is well defined, but it was not beforehand. And the result of the polarization measurements are always correlated instantaneously at the moment of the measurement. Which means if I measure photon A being in H, I know that the photon B is H. Respectively, if I measure photon A being in V, I know that A being in V, I know that photon B is in V too. And this is, because there's no well-defined polarization before the measurement, this occurs instantaneously. And this is a kind of weird effect, which is called entanglement or quantum correlation. So I will always find the polarization ending up in the same detector, say in the respective same detector. So this is, for instance, the basis for quantum K distribution, because now in advance you don't know where each photon will end up, but you know they are correlated, which means once you have registered the detection on each site, the results are correlated and they can be used as a secret key for further classical cryptographic system protocols. And this is independent on the distance or the timing between the detection on whatsoever. So you can try to measure first on the left side, then on the right side, or the other way around to have large distance separating the photons. That will always be preserved. And it's called quantum non-locality because it is a little bit as if what happened on one side influence what happened on the other side. This is not good in physics because according to Einstein's special relativity, the influence cannot propagate faster than light. But in more details, it's that you cannot propagate information faster than light. And in those experiments, because you cannot influence the output of the measurement, you cannot influence the output of the measurement on the other side, so you cannot send information by that way. Okay, this is what I just say. So this contradiction actually was pointed out in the 30s by Einstein, Podolsky, and Rosen in their famous paper, when they say, okay, this is not possible. So it means, according to them, that quantum mechanics is not complete. So it means that the wave function do not fully describe the state of the system. There's something additional, and this something additional is called hidden variables. Now the question was, is it really like this, or is it not, and what are the implications? And for this, we can start to design such thought experiments. So we have the same experiment. So this entangled state of two photons is sent to two players detecting the photons, and you can label the outcome by 1 and -1. So that will be the two possible outcomes on one side, given by variable A, on the other side by variable B. And you can also select the measurement you choose. So until now, I have said, okay, you always measure H and V polarization, which are orthogonal. But you may know that if you think of the polarization of light, you can also measure it according to other angles. So you can measure, for instance, distinguish plus, minus, and plus 45 and minus 45 degree polarization. So this angle will be given here by alpha and by beta. So I'm already a little bit over time, it seems. So, but we can try to shortly finish, I think. So John Bell in 64 came with the solution, let's say, to the Einstein-Podolsky-Rosen paradox, which is the following. So imagine you have the same system as before. So now A and B are the output, as I was mentioning, and X and Y corresponds to the angle. So it's the choice of the measurement that Alice and Bob are doing. And now we assume that there are local variables. So there are some additional local variables which fully determine the output on Alice's side, knowing X. So what we measure is the probability to get A and B, knowing that the measurement settings are X and Y. And now we assume locality. So we say, okay, the probability of getting A and B is local, which means is given by the product of the local probability to get the result A, knowing the measurement X, and assuming the local variable lambda, times the same on both sides. So each measurement only depends on the choices which are made on each side. So this is the locality condition. So we can then, because lambda, we don't have access to them, they are called hidden variables, so we have to average over lambda, over a given unknown probability distribution over lambda. And then Bell's theorem states that this combination, so now the average value of the product of A and B of the measurement is just given by this, it's just the average of A times B with the weight P of AB. So this average value, this combination of average value, where 0 and 1 are the measurements, so X can take the value 0 and 1, Y can take the value 0, and there are two kinds of measurement on each side. So he said, if you assume locality, then this combination has to be smaller than 2. It's just a kind of mathematical statement. And now if we design well-designed quantum experiments, we can see that actually for them, the maximal value we get is 2 times square root of 2, which obviously is larger than that. Which means you can do experiment where this condition is violated, which means that the locality condition is not fulfilled. So there's no local hidden variables. So to do the experiment quantum mechanically, we take the same state as previously. We select now the right angles for the measurement, which are listed here. And then doing the experiment as it was done in 82 by Alain Aspect, Philippe Rangier, they measure, it was the first time when it was, this violation of the Bell inequality, they measure something which is significantly larger than 2. So Alain Aspect was awarded last year with Anton Zeilinger the Nobel Prize actually for such experiment. So this can be generalized actually. You can have such kind of similar system, but with many input, you can think of having many more choices of the experiment, so more value for X and more output at the end. And actually, so it's always described by this kind of the space of the correlation. So these conditional probabilities live in a space where you can then separate the different probability sets into one which is L, which will be described by local variable, one which will be described by quantum mechanics, and some which will not be reached by quantum mechanical system, but will still not allow for faster than light communication. This is called non-signaling. So here it's a reference for a review paper about that. So that was just shortly about entanglement and quantum correlation. So the application of such systems are mainly, I mentioned communication, computation, simulation, sensing. So this is kind of how nowadays quantum technology are classified. And we are more interested in communication, for instance, quantum key distribution. Just as an application for cryptography, I mentioned before. So this is just a quantum random number generator. This is the simplest thing you can do with only one photon or one qubit. But for instance, if you think of those correlations I mentioned before, you can also put boxes around Alice, around Bob, and you can think, so there's one photon detected at Alice, and the other one is sent along a channel to Bob, and from those correlations, they could establish a secret key. And I think I will stop here. So this is really a short introduction. If you have any question, you can always, as Antonio mentioned, contact me. And if some questions comes during the week, then I could maybe next week having a short presentation about the topics or the questions which were raised.
Okay, thank you so much for your introduction to quantum. I'm sure there is a lot to digest for the students so far. So I guess they have a lot to do for this week. So don't forget that you have to skim read all the literature that we uploaded on Zotero. The slides are also uploaded, both my slides and the Professor Stefanov slides. And so you feel free to review them. So they're gonna be very helpful when you are gonna dive in the topics of more the physical aspects, the physics aspects of the articles. I have a question for the students. Who is actually coming from physics? Who has a physics background?
Well, I did some courses on quantum computing, but it was like all centered around the quantum key distribution protocol and stuff like that, because obviously I'm from communication department.
Mm-hmm. Anybody else from physics? Okay, so then it means that our physics advisor will have to will get some questions probably. Okay, so for today is everything. So yeah, don't forget to contact me or Samuel Iniger if you have problems to access Ilias, and read the literature, and don't forget to fill in the sheet with your preference. And then we meet next week again on Friday to form the groups, and then we will have 1 week stop. So for the following Friday we will not meet, so the first group can prepare their presentation, and then from in 3 weeks we start with the talks from the group of students. Okay, so
I'm sorry, I'm a little
much for joining today. I wish you had fun to discover some quantum physics, and I'll see you next week.
Sorry, just one question.
Yes.
Yeah, so when do exactly we come to the next session? I mean, the next seminar.
The next seminar is going to be next week. We just meet for communicating the groups and to finish if there is the intro on quantum, if there is doubts from your side.
Oh, okay, thank you. Thank you.
More questions? Okay, so again, thanks for joining, and I'll see you next week.